important topic is the fault in the power system. So whether you are appearing for the academic exam, for BARC exam, for ISRO exam, for GATE exam, for ESC or any type of competitive exam, the maximum number of questions from the power system generally ask from the fault analysis topic. So from today, in the next 6 days, we will try to cover the fault analysis in the English channel in brief. So I will try to cover the symmetrical fault in the power system as well as the unsymmetrical fault in the power system in brief only. So you can share this lecture all the aspirant of different competitive exams so that everyone will get the benefit of this lecture. So without wasting the time, we just come to our topic. In the today class, I will be discussing about what is the meaning of fault. What do you understand by the fault in the power system? We will also classify the fault in the power system, how we can classify the different type of the fault in the power system. So generally we have a two type of fault, the series fault and the shunt fault. How we can distinguish between the series fault and the shunt fault. Then we will try to find out the fault current whenever the symmetrical fault takes place in the power system. So this is the goal of today class. So let's come to the topic immediately. So whenever we would be discussing about the fault analysis in the power system, the one question that come into our mind is that what is the fault? What is the fault in the power system? What fault is what mistake is committed by the power system? So see, what is the main motive of the power system? So main motive of the power system is nothing but to carry the current from the power plant to the end consumer. If the power system is carrying the current, the normal current from the power plant to the end user, that means our power system is working into the normal condition. But suppose if power system is failed to carry the normal current from the power plant to the end consumer, that means the condition is not normal, the power plant is working into the abnormal condition, or that means we can say there is a fault in the power system. So what happened in this case? Either the current is not flowing from the power plant to the end consumer, or the direction of current has been changed from the normal direction. So basically fault is meaning is nothing but the abnormal condition in the power system. So whenever the fault takes place in the power system, it is not working into the normal condition. That means the value of voltage and the value of current will divert from its normal value. So during the fault time, the power system is working into the abnormal condition. Now, the second question that come into our mind, what may be the major cause of the fault? What may be the main reason that current has diverted from the intended path? What may be the main reason? So main reason of the fault is the failure of insulator. The insulator of the power system has been failed. The lightning, wind, the tree falling on the line, it may be because of the birds, or the line breaks, vehicle colliding with the tower line. So there may be the different cause of the fault. So we can say if we classify the fault, we can classify fault into the two category. The fault may be either open circuit fault or it may be the short circuit fault. The open circuit fault is also called the series fault. Similarly, the short circuit fault is called the shunt fault. So it may be the open circuit fault or it may be the short circuit fault. The open circuit fault further classify into the three category. It may be the one conductor is the open circuit, two conductors become open circuit, and the three conductors become open circuit. So whenever the open circuit fault occur, that means the current is not flowing from the power plant to the end consumer. So it may be either the open circuit in the one conductor, or it may be the open circuit into the two conductor, or it may be the open circuit into the three conductor. But in our syllabus, we generally study the short circuit fault. The short circuit fault is the most important. So we will try to cover the short circuit fault into the detail. So short circuit fault, which is also called the shunt fault, can be classified into the two categories. It may be the symmetrical fault or it may be the unsymmetrical fault. So we will focus our discussion only on the shunt fault or the short circuit fault. That means in the next 6 days, we will try to cover the symmetrical fault as well as the unsymmetrical fault. So what is the main difference between the symmetrical fault and the unsymmetrical fault? Suppose when power system is working into the normal condition. So when power system works in the normal condition, that means our system is a symmetrical one, or you can say our system is a balanced system. What do you understand by the balanced system? If our source is balanced and our load is balanced, that means our three-phase system is a symmetrical or the balanced system. So in the symmetrical fault, even if the magnitude of current has been changed from its normal value, but even in that case, the system will remain into the symmetrical condition, or the system will remain into the balanced condition. That means the current at the time of fault in all the three phase will equal in magnitude, and there will be a phase difference of 120 degree between the A phase, B phase and the C phase current. So in the symmetrical fault, what do you understand by symmetrical fault? Even during the fault condition, our system is remained into the balanced condition. The symmetrical fault is a fault which involve all the three phase. If the fault involve all the three phase, it is called the symmetrical fault. So there may be the two type fault in the symmetrical fault. One is the triple line fault and second is the triple line to ground fault. Clear? The symmetrical fault, which was the example of the shunt fault, it may be two type, triple line fault and the triple line to ground fault. If all three phase are short circuited with each other, it is called the triple line fault. In A phase, B phase and the C phase, all is become short circuited, it is called the triple line fault. The triple line to ground fault is nothing but if all three phase is short circuited and it is also short circuited with the ground, it is called the triple line to ground fault. When we come, see, at the time of fault, if the current in A phase is IAF, current in B phase is become IBF, and the current in the C phase is become ICF. IAF, IBF and the ICF. In case of symmetrical fault, the system will remain into the balanced condition. That means the phasor sum of all current IAF, IBF and ICF. The phasor sum of all three current is equivalent to 0. So if phasor sum of all three current is equivalent to 0, that means the no current is flowing through the ground. So you can say whether it is a triple line fault or triple line to ground fault, both are basically the same type of fault, because even if the ground is connected here but no current is flowing through the ground. Okay, now we come to the unsymmetrical fault. So what is the meaning of unsymmetrical fault? See, the unsymmetrical fault is a fault which involve either one phase or two phase. That means if the fault does not involve all the three phases, these type of fault is called the unsymmetrical fault. It involve either one phase or it involve the two phase. So there may be the different type of unsymmetrical fault. One is the line to ground fault. That means one conductor is short circuited with the ground. The line to ground fault is the least severe fault. That means during line to ground fault, whenever the line to ground fault occur at the transmission line, the magnitude of the fault current will be minimum. So it is a least severe fault, but the chances that the line to ground fault occur is the 70%. That means the majority fault that occur into the power system are the line to ground fault only. Now the second type of fault is line to line fault. If two phase conductor, either A or B phase or B or C phase or C or A phase, are short circuited with each other, this type of fault is called the line to line fault. So the probability of line to line fault is 15%. The occurrence of the line to line fault is nothing but the 15%. Now the third type fault is called the double line to ground fault. If two phase conductor are short circuited with each other and it is also short circuited with the ground, this type of fault is called double line to ground fault. The probability of occurring of double line to ground fault is the 10%. So the maximum chances of the fault occurrence is the line to ground fault, then double line fault, and then double line to ground fault. Now, how we can distinguish between the shunt fault and the series fault? In case of shunt fault, the current will be increased and the voltage will be decreased. During normal condition, at any point, the magnitude of voltage and the magnitude of current will be the normal in value. But whenever the shunt fault takes place into the power system, the voltage will be reduced and the current will be increased. This is the characteristic of the shunt fault. Clear? How this will happen? Suppose see, in the normal condition we have a source and through the transmission line a load is connected. I am just drawing a single line diagram. So in this complete circuit, Z is my load impedance and there is a some impedance of the transmission line. So normal current is flowing into the system in the transmission line, that will be the value of E upon Z plus some impedance of the transmission line. Suppose if the shunt fault takes place here, now what will happen? The impedance of this path will be reduced because it does not include the load impedance and it will include only the impedance of transmission line up to this value, up to this line. So the impedance will be reduced. So what happened? The current will be increased. The value of current will be increased. So current will be increased here and at this point the voltage is become 0. At any other point the voltage will nothing but the voltage drop from the fault point to that point only. So the shunt fault is characterized by the increment of current and the decrement of voltage, because the impedance of the fault current, the impedance will be reduced and the magnitude of fault current will be increased here. Now in case of series fault, it is just opposite to the shunt fault. Whenever the series fault takes place into the power system, the voltage will be increased because at the open circuit the voltage is become equivalent to the source voltage and the current is become 0. That means the current will reduce and the voltage will be increased in case the series fault takes place into the power system. We will limit our discussion only for the shunt fault. Now, the question that come in our mind is that why we are analyzing the power system during faulty condition? Because whenever the fault takes place into the power system, it is not working into the normal condition. So why we want to find out the value of fault current or the fault MVA? Because it is not the normal condition of the power system. Clear? See, there may be the two type of analysis in the power system. One is called the load flow analysis and second is called the fault analysis. In the load flow, we study the power system when the power system is working into the normal condition. But into the fault analysis, we are studying the power system when power system is working into the abnormal condition. So why we want to find out the value of fault current and the fault MVA in the power system when it is not working into the normal condition? The main thing is that by using the fault analysis, basically we want to find out the rating of our protective equipment. See, power system have the protective equipment that these equipment protect the power system during abnormal condition. The main two component of these protective equipment are the circuit breaker and the relay. Relay sense the fault and whenever the fault takes place, circuit breaker isolate the faulty section from the normal section. So the main two components of the protective equipment are the relay and the circuit breaker. So by doing the fault analysis, we will find out the rating of relay as well as circuit breaker. Now relay, we all know, relay just sense the fault. It does not protect the power system from any faulty condition. It just sense the fault. So relay is designed so that it should be able to sense the minimum value of the fault current. Because if relay can sense the minimum value of fault current, definitely it will able to sense the high value of current. See, every relay have the trip value. Suppose during the faulty time, the fault current can vary 200 ampere, just I am giving an example, to the 5000 ampere for the different fault. The fault current may vary from the 200 ampere to the 500 ampere. So whenever we will select the relay, I will select the relay that it will able to trip even if the 200 ampere current is flowing through the relay. Because if it is able to trip at 200 ampere current, it will definitely trip at the 5000 ampere or any current which is above 200 ampere. So relay is designed the minimum value of fault current. It should be able to sense the minimum value of fault current, because if it is able to sense the minimum value of fault current, it will definitely sense the high value of fault current. Now, but circuit breaker, the rating of circuit breaker is opposite. The rating of circuit breaker should be such that it should be able to break maximum value of the fault current. Because if the contact of circuit breaker is able to separate out for the maximum value of fault current, it will definitely break the minimum value of fault current. Suppose any circuit breaker, the circuit breaker have a two contact. One is fixed contact and second is the movable contact. If the fixed contact and the movable contact of the circuit breaker is able to break the fault current of the 5000 ampere, no doubt it will definitely able to break the fault current of 200 ampere. So relay is designed as per the minimum value of fault current, but the circuit breaker is designed for the maximum value of fault current. So by using the fault analysis, we will find out the value of fault current, and according to that, we will design the circuit breaker and the relay. Okay. Now, what assumption generally we take during the fault analysis? Whenever we will calculate the value of fault current or the fault MVA in the fault analysis, we will take some assumptions. What is these assumptions? We will assume that all the EMF of the generator, the EMF of the all generator are 1 angle 0 degree. That is the nominal value or the rated value. So all generator are giving power at the rated condition. So the system voltage is at the nominal voltage normally. We assume that the system is at no load condition. That means until unless it is given to you, you will assume at the time of fault, the load current was equivalent to 0. That means before the occurrence of fault, no current is flowing through the power system. Why we assume this one? Because the normal current, the value of fault current is very, very high as compared to the value of load current. So generally we neglect the value of load current as compared to the fault current. See, if we assume that our system is working at the no load condition, this is my source, this is my source, and through the transformer and the transmission line, we are transmitting the power to load. This is my load. Suppose if I assume that no current is flowing, that means it is working at the no load condition, and the EMF of the source is 1 angle 0, that is the nominal value. Because no current is flowing, that means there is a no voltage drop. So at any point, if you find out the voltage at any point, it will be nominal in value only. at any point in the power system, the voltage will be nominal. If you assume that the power system is working at the no load condition. This is our first assumption that we take to calculate the fault current. The second assumption is that we generally neglect the shunt branch of the transformer. See, whenever we draw the equivalent circuit of the transformer, it is like this. It has the series branch and it is also having the shunt branch. Series branch as well as the shunt branch. Shunt branch has the two elements. One is RC and second is XM. Magnetizing reactance and the core loss resistance. And the current flowing into the shunt branch is nothing but the I naught or the no load current. Generally, the value of no load current is only the 2 to 6% of the rated current in case of the transformer. So we can neglect the value of no load current as compared to the rated current. So we does not consider any shunt branch parameter. It will make our calculation easy. Clear? Now, third assumption we do, the shunt capacitance of the transmission line is neglected. See, generally, the transmission line is represented like this. It is also having some series branch parameter and some shunt branch parameter. This is the resistance of transmission line, reactance of transmission line, capacitance and the conductance. The value of conductance is almost 0. So generally we do not take the conductance into the account. But for fault calculation, we also neglect the value of shunt capacitance. That means we do not consider the parallel component of the transmission line. Now, the system resistance is neglected, only the inductive reactance of transmission line is taken into account. Because if you compare the value of resistance and the value of reactance of the transmission line, the value of resistance of the transmission line is very, very less as compared to the value of reactance, because generally our conductor is made of the aluminum, which have the very low value of resistance. So we also neglect the value of resistance. So we will represent the transmission line only as a reactance. So at the time of fault calculation, to calculate the fault calculation, we will consider the transmission line as a reactance only. Sir, chapter name is the fault analysis in the power system. Clear? Okay. Now, the next assumption we do for the fault calculation is that the current carried out by the load under fault condition is ignored. See, I already told you, we assume before occurrence of the fault, our system is working at the no load condition. Generally what happen? No doubt there will be some load here. So the load current would be flowing into the transmission line before occurrence of the fault. But the value of load current is very low as compared to the value of fault current. So we generally neglect the load current. Unless it is given into the question, we will always neglect the value of load current. So the current carried out by the load under the fault condition is ignored. That means we will assume before occurrence of the fault, no load was connected into the power system, so that the pre-fault voltage will be maximum. If no current is flowing here, that means no voltage drop is taking place into the transmission line. So everywhere the voltage will remain same, and whenever you find out the fault current, it will be give you the maximum value. That means in this assumption, when you find out the value of fault current, it will definitely more than the actual value of fault current. So we are taking the worst case analysis. That means the calculated value of fault current will be more than the actual value of fault current. So we are analyze the power system in the worst case scenario. Clear? Now, the next assumption we do for the calculation of fault, during fault, synchronous motor is act like a synchronous generator. Can anybody can tell me how this happened? Why during the faulty time the synchronous motor will act like a synchronous generator? Anybody? Why during the fault condition the synchronous motor is become synchronous generator? See, what is the main difference between the synchronous motor and the synchronous generator? In the synchronous machine, whether it is a motor or generator, we have a two main component. One is the stator, second is a rotor. The stator of synchronous machine is also called the armature, and the rotor of synchronous machine is called the field. So see, we have a two type of winding. One winding is called the field winding. The rotor may be either cylindrical type or the salient pole type. And this is my stator, which have the three phase winding. We excite its field winding with the DC supply, which create the magnetic field. So we excite this field winding with the DC supply, which create the magnetic field. In case of motor, what will happen? We supply the stator winding with the three phase AC supply. So now we have two type of flux. One flux is created by the armature winding. Second flux is created by the field winding. Then we rotate the rotor with the prime mover at the synchronous speed. So now we have a two magnetic field which is rotating at the synchronous speed. And by the interaction of this, the electromagnetic torque is created. So it is start rotating. This is the principle of synchronous motor. In case of synchronous generator, what happen? We excite the rotor with the field winding and rotate it by the prime mover, and it will give you the three phase electrical power. Now what happened? Suppose this is our system. We have a synchronous generator, and at any place in the power system we will also having the synchronous motor. So in the normal time, the electrical power or the electrical current is flowing from synchronous generator to synchronous motor, and its rotor is rotating. That means we are giving the electrical energy and it is giving out the mechanical energy. Now what happened? The shunt fault took place somewhere here. So whenever shunt fault took place here, now the current is not going from source to load. Now this generator is feeding the fault current only. It is start feeding the fault current. So what happened? Now the no current flowing into the armature winding, but its field winding is still excited by the DC. That means the magnetic field is still present at the between the stator and rotor. And since due to inertia, its rotor is rotating. We are not rotating the rotor by using the prime mover, but before occurrence of the fault, it was a synchronous motor. So the rotor was rotating, and due to inertia, it will keep rotating for the some times. So we have a magnetic field and the rotor is rotating. That means that this synchronous machine now it will start working as a synchronous generator. So synchronous motor will convert into the synchronous generator. Once it convert into a synchronous generator, that means now it will start giving the electrical power. So this will also feed the fault current. So not only the synchronous generator, but synchronous motor is also feeding to the load current. See, so you have to take care of this at the time of fault. If the synchronous motors are present into the power system during the faulty time, the synchronous motor is become synchronous generator because it has the store energy, because due to inertia it is rotating, and this energy convert into the electrical energy. So it also supply to the fault current. So overall the value of fault current will be increased. But it occur only in case of synchronous generator. Suppose if the induction motor is present, whether this induction motor will convert into the induction generator or not. Can anybody can tell me? If in the power system induction motor is present during faulty time, what happened to the induction motor? What happened to the induction motor? See, the main difference between the induction motor and the synchronous motor is that the synchronous motor is a doubly excited machine. So its field winding is also excited. So even at the time of fault, we are having the magnetic field in the air gap. But our induction motor is a singly excited motor only. Its rotor is not excited by a separate supply. So suppose whenever the fault in the normal time, the current is flowing from the synchronous generator to the induction motor. And this current is creating the rotating magnetic field, due to which the rotor of induction motor was rotating. But whenever the fault took place somewhere here, now the direction of current has been changed. Now the synchronous generator is feeding to the fault only. So the no current is flowing to the induction motor. If no current is flowing at the stator of induction motor, that means the magnetic field is become zero, because it is not a doubly excited motor. Its rotor is not excited by a separate supply. So whenever no current is flowing into the stator side, the magnetic field is become zero and induction motor will stop. So it does not participate to increase the value of fault current, but the synchronous motor participate to increase the value of total current. Clear? So since stator current is become zero, so flux in the air gap in case of induction motor is become zero. So it does not supply any fault current. So that's why we say if the synchronous motor is present in our power system, it creates the stability problem. But if the induction motor present, it does not add to the stability problem of power system. Now one more thing, variation of speed of alternator or frequency variation are ignored. We all know the frequency of power system is basically depend upon the speed of rotor of our alternator or synchronous generator, because we know that Ns is 120 F upon P. So frequency is nothing but the P into Ns upon 120. So frequency of power system is depend upon the pole speed. So whenever the speed will change at the time of fault, no doubt the frequency will be changed. No doubt it will be changed. But whenever we calculate the fault current and whenever we are doing the fault analysis, we do not consider this variation of frequency. We do not consider the variation of frequency at the time of fault. So all these assumptions we are doing. Why we are doing all these assumptions? Just to make our fault analysis simple. This is the main reason. If we do not, we take all these things into account, then the calculation of fault current is become very, very difficult. To make the calculation easier, we are doing all these assumptions. That's all. Now, today I will discuss about the symmetrical fault. I told you what is the symmetrical fault. Before occurrence of the fault or during the normal condition, our power system is always a balanced system. We have a balanced source and the balanced load. So in the balanced system, the phasor sum of all three phase current is equivalent to 0. But whenever the symmetrical fault takes place, what is the symmetrical fault? If in any fault all three phases are involved, it is called the symmetrical fault. If all three phases are involved during the fault, it is a symmetrical fault. I already told you it may be two type, triple line fault, that means all three phases are short circuited, or triple line to ground fault, that means all three phases are short circuited and it is also short circuited with the ground. Now the three phase fault is a very rare, that means the chances of occurrence of three phase fault is a minimum. It is a very rare fault. There is a very rare chances that this type of fault takes place into the power system. But it is very important, even if the fault are rare, but it is very important. Why it is very important? Because whenever the three-phase fault occur into the transmission line, I am talking about the transmission line, it is the most severe fault. Most severe fault means at the time of three-phase fault, the value of fault current is the maximum. And with the value of maximum fault current, we decide the rating of circuit breaker. So the rating of circuit breaker is decided by the symmetrical fault only. Clear? Even if it is rare, it is a very important fault because the rating of circuit breaker is mainly governed by the symmetrical fault. I already discussed this thing. The rating of circuit breaker is decided by the maximum value of fault current, and the rating of relay is decided by the minimum value of fault current. Okay. Because the symmetrical fault is the most severe. Severe means whenever the three-phase fault occur at the transmission line, the value of fault current will be maximum. Clear? So symmetrical fault analysis are simple, but it is very easy to find out the fault current when symmetrical fault took place in the power system. Why? Because during the fault, the circuit are balanced. It is a symmetrical fault. Even if during the faulty time, our system is remain into the balance condition, and we all know it is very easy to find out the value of current if the three-phase system is remain into the balance condition, because we can do the per phase analysis. We can convert the three-phase circuit into the single-phase circuit only, because in all the three phase the value of current will remain same and there will be the difference of 120 degree in phase. Clear? So they are simple because during the fault circuit are balanced. So calculation may be done on the per phase basis. So analysis of the symmetrical fault is very easy as compared to the analysis of unsymmetrical fault. All these points are clear of symmetrical fault. See, now let us analyze the symmetrical fault. Suppose we have a alternator or the synchronous generator which is generating the three-phase electrical power. We have A phase, B phase and the C phase. In normal condition, the three-phase power will be flowing to the three-phase load, or maybe it may be the three single-phase load. So we have a three-phase load here. This is our normal condition before occurrence of the fault, you can say. And the current that is flowing from the source to load will be IA, IB and IC. The current will be, all current will be same, and there will be the phase difference of 120 degree. Suppose generally we do not consider the load current. So we will assume before occurrence of the fault, no current is flowing in the system. Now what happened? The triple line to fault occur. That means all three phase circuit are become short circuited. A phase, B phase and the C phase is become short circuited. Now before occurrence of the fault, no current was flowing. This I am assuming. After occurrence of the fault, current into the A phase is become IA, IB and the IC. Because it is a symmetrical nature of fault, that means the magnitude of all three phase current would be equal and there will be a phase difference of 120 degree. See, this I will prove. During the three phase fault, neither zero sequence nor negative sequence current will flow. Only positive sequence current flow during the three phase fault. This I am proving. Suppose, see, if we apply the Kirchhoff current law here, this is a node, all node is connected. So IA, IB and IC, the sum is equivalent to 0. Clear? So see, during fault, we assume that the current in A phase is the IA, current in B phase is the IB and current in the C phase is the IC. If you apply Kirchhoff current law here, the magnitude of IA plus IB plus IC, it is equivalent to 0. It is equivalent to 0. And see, at this point type, all three nodes are connected. That means the voltage here, the voltage here and the voltage here are equal. That means VA is equivalent to VB, VB is equivalent to VC. Clear? So VA is equivalent to VB and it is equivalent to VC. So this is the relationship between the phase voltages and the phase current. Now, are you aware about the A operator? A operator. Like J operator, we use the A operator. What is the value of J? J is nothing but its magnitude is 1, its angle is 90 degree. That means if you multiply any phasor with the J, the magnitude of phasor will remain same, but it will rotate 90 degree into the anti-clockwise direction. Similarly, A operator is nothing but its magnitude is 1, but its angle is 120 degree. That means whenever we multiply any phasor with A operator, this phasor will rotate 120 degree in anti-clockwise direction because it does not change the magnitude of phasor, but it simply rotate the phasor 120 degree positively, means 120 degree into the anti-clockwise direction. So whenever we multiply any phasor by A operator, it will rotate phasor by 120 degree in anti-clockwise direction. Clear? Suppose, let us assume that this is our phasor. Just assume that it is a VA. If I multiply VA phasor with A operator, what will happen? It will rotate the phasor by 120 degree into the anti-clockwise direction. So this is become A into VA. Because I multiply VA phasor by A operator, it will rotate this phasor by 120 degree into the anti-clockwise direction. Clear? Now see, now we come to this. We have 3 currents in the symmetrical fault. The current, our system is symmetrical, means the magnitude of all 3 current are equal and there is a phase difference of 120 degree. So let us draw IA, IB and IC. So we have 3 current IA, IB and IC. This is IA, IB and IC. IA, IB and IC. Phase sequence is ABC, A, then B and then C. Now I told you, if I multiply this IA by A operator, then this phasor will rotate 120 degree into the anti-clockwise direction. That means IC is nothing but is equivalent to A into IA. If I further multiply AIA phasor by A operator, it will further rotate this phasor 120 degree into the anti-clockwise direction. So this is nothing but the A square into IA. This is the A square into IA. So I have converted all 3 phase current in term of A phase current. This point is clear? Okay. Now see, I will find out the sequence current, means the positive sequence current, 0 sequence current and the negative sequence current. What magnitude of sequence current flow whenever the symmetrical fault takes place into the power system. So see, we all know that the IA0, IA1 and IA2 is 1/3 IA, IB, IC, sorry, 1 1 1 1 a square 1 a square a IA, IB and IC. This is the relationship between the phase current and the sequence current. So now let us find out one by one the value of IA naught, the magnitude of zero sequence current. It is nothing but 1 upon 3 IA, IB and IC. IA plus IB plus IC. This is clear. Now I just told you the IA plus IB plus IC, the phasor sum of all these current is equivalent to 0. It has become 0. That means IA 0 is equivalent to 0. So no zero sequence current will flow in case of symmetrical fault. No zero sequence current will flow. Clear? Now let us come to whether the negative sequence current will flow or not. Let me find out. I am finding out the negative sequence current IA2. So IA2 1 upon 3 IA plus A square IB plus AIC. A square IB plus A into IC. This is the value of IA2. Now let us convert all phase current into IA terms. IA. Now IB is A square IA. IB is A square IA. So replace IB by A square IA. Now IC is equivalent to AIA. AIA. So 1 upon 3 IA plus A4 IA plus A square IA. Now see, we know that AQ is equivalent to 1. We all know AQ is equivalent to 1. So A4 is nothing but the A cube into A. Because AQ is equivalent to 1. A4 is nothing but the A only. It is 1 into A. So if I put this value here, 1 upon 3 IA. Now it is become AIA, A square IA. If I take IA as a common term, so 1 plus A square. Now we all know in case of A operator, 1 plus A square is nothing but it is equivalent to 0. So this is 0 only. This is 0. So IA2 is also become 0. IA2 is also become 0. So that's why we can conclude that whenever the symmetrical fault takes place in the power system, neither negative sequence current nor zero sequence current flow into the system. So that's why we can say no zero and no negative sequence current flow. That means only positive sequence current will flow. Now what is the value of this positive sequence current? Let's find out. IA1. What is the value of IA1? So IA1 is a 1 upon 3 IA plus AIB A square IC. Now what is the value of positive sequence current? It is IA plus A into IB plus A square into IC. Clear? From this. Now IC is AIA, IB A square IA. So I will put the value of IB and IC in term of IA. IB is A square IA. So it is A square IA. And IC is AIA. AIA. So 1 upon 3 IA plus A cube IA plus A cube IA. Now we know A cube is nothing but the 1. A cube is 1. So 1 and 1, IA plus IA. So it is become IA1, 1 upon 3 IA plus IA plus IA. 3 IA divided by 3 is nothing but IA. So the total current that is flowing in the system is having only positive sequence component. So always remember, whenever the symmetrical fault happens into the power system, the symmetrical fault means the fault during which all the three phases are involved, then no zero sequence, no negative sequence current flow, only positive sequence current flow. Now I will find out what will be the magnitude of this positive sequence current that is flowing into the circuit, because it is the same as the fault current. This positive sequence current is same as the fault current, because only this current is flowing during the faulty time. Okay, so see, VA, VB, VC. Let's find out the value of VA1. So value of VA1, 1 upon 3. Just find out in term of phase voltage, VA, VB, VC. VA, A, VB plus A square VC. Now, during the symmetrical fault, the VA is equivalent to VB and it is equivalent to VC. So VA is equivalent to VB, VA only, and VC is also equivalent to VA only. So 1 upon 3, VB is equivalent to VA, VC is also equivalent to VA. So 1 upon 3 VA, 1 plus A square. And we all know 1 plus A square is nothing but the 0. So VA1 is equivalent to 0. VA1 is equivalent to 0. So during the symmetrical fault, the terminal voltage of the positive sequence circuit is equivalent to 0. No negative, no zero sequence network is coming into the picture. Only positive sequence circuit is coming into the picture. Now, we all know what is the positive sequence network. The positive sequence network is like this. It is having a source in series with a positive sequence impedance. Clear? Suppose source, positive sequence, induced EMF. This point is called the VA1. VA1 is nothing but the terminal voltage of positive sequence network. Now we have just proved this VA1 is equivalent to 0. 0 means it is like short circuit. It is like short circuit only. It is like short circuit. So this is the short circuit. The current flowing into the positive sequence network is nothing but the IA1, and we just proved that IA1 is equivalent to IA and it is the same as the fault current. So value of IA1 we can find out from this. The value of IA1, which is also is equivalent to the fault current, is EA1 upon Z1. If we assume that the no load current is equivalent to 0, then EA1 is a nominal value, which is the 1 angle 0 degree. So it has become 1 angle 0 degree divided by Z1. By using this formula, we can find out the value of fault current. Any doubt? So no negative sequence network, no zero sequence network is coming into the picture. Only the positive sequence network come into the picture during the symmetrical fault. And we just proved that the VA1 is equivalent to 0. This is our symmetrical positive sequence network of the alternator. So in this way, we can find out the value of fault current. Now, here we just assume it is a bolted fault. If the fault does not involve any impedance, it is called the bolted fault. Clear? If fault does not involve any impedance, it is called the bolted fault. If the fault is having some impedances, because whenever the arc is created, suppose the triple line to ground fault occur, that means whenever the short circuit is occurring, there is a arc. The arc is having its own resistance. That means the fault is having some resistance or impedance. No doubt, mostly the fault impedance is resistive in nature only. Okay. So whenever the fault is having some impedance, in this case, the value of fault current is having EA1 divided by Z1 plus ZF. If we neglect the no load current, in that case, EA1 will be equivalent to 1 angle 0 degree. Z1 plus ZF. So by using this formula, we can find out the value of fault current in case of symmetrical fault. This point is clear? This point is clear? So in tomorrow class, I will take one example, then I will discuss how to find out the fault current whenever the symmetrical fault takes place. These are the steps, but now the time is not sufficient to discuss this thing in detail. So I will continue our discussion from this slide in tomorrow class. So any doubt in the symmetrical fault? The tomorrow class we will complete the symmetrical fault, and from day after tomorrow I will start the unsymmetrical fault. So finally, I come to the conclusion of this lecture, the 2-minute summary. In today's class, we have discussed what is the basically meaning of fault in the power system. A power system is failed to deliver normal current from power plant to the end consumer. That means it is not working into the normal condition. There is a fault into the system. After that, we classify the fault. We have a 2 type of fault, shunt fault and the series fault. Shunt fault is called the short circuit fault. Series fault is called the open circuit fault. We are keeping our discussion only for the shunt fault. Shunt fault we can further classify into 2 categories. That is the symmetrical fault and the unsymmetrical fault. In the symmetrical fault, all 3 phases are involved. In unsymmetrical fault, either 1 phase or 2 phases are involved. Now, after that, I have discussed what assumption we do during the fault analysis. This assumption has been done just to reduce that time to calculate the value of fault current. That's all. Then finally, I derived the formula to find out the value of fault current. if the symmetrical fault occur into the power system. How to find out the value of fault current in case of symmetrical fault? Clear? So we'll meet tomorrow at the same time, 7 p.m. to 8 p.m. and we will continue our discussion on the symmetrical fault. Till then, good night everyone.